Hello, and welcome to Backer Breaks It Down. In this episode, we're going to explore power functions. You're probably wondering what's a power function. The comic is illustrating two power functions. But what do you think? Okay, so on the left, I have examples of power functions, and on the right, examples of non-power functions. So what exactly is a power function? A power function can be written in the form f of x is equal to k times x to the a power. Now, k and a are non-zero constants. K is called the constant of variation. And a, well, that's your power, that's your exponent. Now, the key to power functions is the exponent can take on any real number value. So what does that mean? Well, taking a look at our examples of power functions, one exponent is 2. 2 is a real number. Here we have an exponent of -3. Here we have an exponent of 5/3, -1/2. Okay. So basically, when they say any real number value, they mean positive, negatives, both are okay. Integers, whole numbers, fractions, decimals, those are okay too, right? So a power function is a monomial, so it's a single term, okay? And the exponent is going to be any real number. So that's why over here, this is not a power function because the exponent is a variable. This is not a power function because there are two variables, x and y, okay? This isn't a power function because it's made up of more than one term. So in examples 1 through 3, it says determine whether the function is a power function. Okay, so remember power functions look like this, k times x to the a power, and the exponent can take on any real number value. Okay, so number 1 is a power function. So is number 3. Number 2, look at your exponent. It's a variable. This right here is an example of an exponential function, which we studied previously, okay? So it's all about the exponent. It has to be a real number in order to be a power function. Now, we're going to encounter functions that aren't written as power functions initially. And so we can write a function that doesn't at first glance look like a power function. We can write it as a power function using our properties of exponents. Okay, now there are quite a few properties of exponents here. You've got the product rule, okay, and the product rule I would use whenever I'm working with, well, a product. So whenever you're multiplying exponential expressions like this, x to the -3rd power times x to the 7th, you can use your power rule. And basically, your new exponent is going to be the sum of the exponents. Then there is the power rule, okay? The power rule says when an exponential expression is raised to a power. So here is an example of what that would look like. We're going to multiply the exponents. So -3 times 4, well, that's how they're getting -12. You could have a product raised to a power. So when a product is raised to a power, raise each factor to that power. So looking at this one, here I have a product, -2 times y, and I'm raising it to the 4th power. Notice they're taking -2 to the 4th power and y to the 4th power. And that gives us 16 y to the 4th power. The quotient rule. It says when dividing exponential expressions with the same base. So here I have x to the 3rd divided by x to the 7th. Okay, we are going to subtract the exponents. And then we have a quotient raised to a power. So when a quotient is raised to a power, raise the numerator to that power and the denominator to that power. So if you look here, you have the quotient -3 over x. And they're raising that quotient to the 3rd power. So they're taking -3 to that 3rd power x to that third power. Negative 3 to the third power is negative 27. Okay. Negative 27 over x to the third power is not a power function. We're going to rewrite it using a negative exponent. Okay. So let's write these functions as power functions. So when I look at number 4, it's not looking like this, k times x to the a power. The problem is the denominator. Okay, so in the denominator, I have that x to the 5th. So I have this rule here that says that I can take that power in the denominator and I can move it. Now, when I move it, the exponent's going to change signs. So notice right now, x to the 5th power, it's in the denominator, it's all positive and happy. And when I go and I bring it up to the same level as the 6, that exponent will change signs. So it was happy in the denominator, but when I took it out of the denominator, its attitude changed and became negative. And 6x to the negative 5th is a power function. Looking at this one, I have to, first see what's going on here. So here, notice I have 3 times x to the negative 2nd, okay, raised to the 2nd power. So this is what I'm working with here. I'm working with that product power rule. So I have to share the exponent. So I have to take the 3 to the 2nd power, and I have to take the x to the negative 2nd. I have to take that also to the 2nd power. So you're sharing the exponent with those two factors. Now 3 to the 2nd power is 9. When it comes to the x to the negative 2nd power squared, that's this power rule. I'm taking something with an exponent and raising it to a higher power, so I'm going to multiply my exponents. So negative 2 times 2 is negative 4. In number 6 here, I see a quotient. So this is what I'm seeing when I look at number 6, because I have 4x to the 4th divided by 5x to the negative 5th. Now the 4/5, that's just going to be that k value. And then when it comes to x to the 4th divided by x to the negative 5th, if I use this rule, I'm going to subtract my exponents. So 4 minus negative 5 is 9. So now they start to get a little bit trickier, I guess. So when I look at number 7, I see a quotient, 2 over x to the 4th being raised to a higher power. So I want to use this rule right here that will take that quotient to the higher power. Notice that they're sharing the exponent. So if I do that, I'm going to take 2 on top to the 3rd power. And on the bottom, I'm going to take x to the 4th, and I'm going to raise that to the 3rd power. So 2 to the 3rd power is 8. On the bottom, I have x to the 4th to the 3rd power. So that's this rule, that power rule, where I multiply my exponents. So 4 times 3 is 12. Now, right now, this is not a true power function. I'm not allowed to leave the x to the 12th in the denominator. So I need to use that negative exponent rule. This is the rule that allows me to take what's in the denominator and bring it on up. Okay, so 8's fine where it's at. X to the 12th is being moved, and look at, wasn't too happy about that. Its sign changed. So 8x to the negative 12th is the power function here. Number 8, this looks kind of intimidating. I'm dealing with square roots, okay? Now, when it comes to the square root of 25, like I know the square root of 25 is 5, so I'm just going to straight up do that. On the bottom, I need to take the square root of x to the 5th. Now, back when we were working with exponential functions, we worked with like this rule here. And this rule allows me to rewrite radical expressions using rational exponents. Now remember, square roots have an index of 2, all right? So that means the square root of x to the 5th would be x to the 5/2. Because this m over n, m is the original exponent, n is the index. And then just like the previous problem, I can't go leaving that variable on the bottom. I have to bring it on up. And when I do that, the sign will change, making it negative 5/2. And then finally, looking at number 9, wow, there seems to be a lot going on here. Okay, so let's just take this piece by piece. So when I look at the numerator, I see a power raised to a higher power, which means that I'm going to multiply those exponents together, giving me x to the negative 12th power. On the bottom, what I see is 2x to the third times x squared times x. So I'm going to use that product rule, and I'm going to add all those exponents together. So I have the 2, and then I'm going to have x to the 3 plus 2 plus 1, 6th power. So now what I have is a quotient. So I'm looking at this right here. And so it says I should subtract the exponents. Well, when it comes to that k value, that constant, there's an invisible one here. So basically 1/2 is your k value. When it comes to your new exponent, when we go negative 12 minus 6, we get negative 18. So 1/2 x to the negative 18th power is our power function. So power functions are functions of the form f of x is equal to k times x to the a power. K and a are non-zeros. K is called your constant of variation. A, well, that's your power. It's your exponent. And most importantly, the exponent. It can take on any real number value. So positive, negative, integers, whole numbers, fractions, decimals. That's what they're talking about. And that is how Becker breaks it down.